demo for lesson 31 for college algebra. We're going to talk about exponential growth and decay models. They come in two equivalent forms. We have a naught times b to the t, or a naught times e to the kt. These are completely equivalent. Anytime that you're asked to write a function that models an exponential growth or decay situation, you can choose which one of these you want to use. And just make a smart choice based on what's given in the problem. If you see the word continuous, you're going to choose the e to the kt model because the continuous growth rate is k, and then b is called the growth or decay factor. But you can convert. So even if you were given the continuous growth rate and you wanted to write it in this format for some reason, you could solve for the b. B is just e to the k, and k is just the ln of b. So a naught, a sub 0, it always represents the initial quantity, the amount that you start with at time 0. B is your growth or decay factor. When b is bigger than 1, you have growth. When it's a small number between 0 and 1, we have decay. And k is called the continuous growth or decay rate. It's often expressed as a percentage. And when you put it into the formula, you change it to a decimal. So for example, we have there was an Ebola outbreak in West Africa in 2014. So on September 3rd, there were an estimated 3,902 cases. And then between September 3rd and November 18th, the number of Ebola cases grew at a continuous growth rate. So we see that word continuous. Then I'm going to use the e to the kt model. So it says construct two equivalent models. So I've got a of t equals a naught e to the kt. That's one model, and that's what I'm going to start with because they gave me the continuous growth rate. And then my other model is a of t is a naught times b to the t. Okay, so we've got the continuous growth rate. Construct two equivalent models for the outbreak between September 3rd and November 18th. All right, so my initial amount is 3,902. My continuous growth rate is 1.252%. I'm going to put that in as a decimal for k. So that would be 0.01252 t. So there's one model. And then in my other model, I want to, a naught is the same. So a of t equals 3,902. But then b is related to k in that, go up to my formulas here, b equals e to the k. So I'm just going to go to my calculator, tap in e to the 0.01252. Most calculators have an e button, 0.01252. And I get 1.0125. That's my growth factor. Um, 995. I'll just round it there to the t. All right, so it turns out November 18th represents day 83. How many Ebola cases does this model predict for December 5th, which is day 100? So I just want to plug 100 into my model, and I can use either one. I'm going to use the first one because I rounded a number in my second model. This model here, I rounded b, so I think that this one's going to be more accurate. So I'm going to plug 100 into my first model. So I have 3,902 times e to the 0.01252 times 100. And let's see what my calculator says here. 3,902 times e to the 0.01252 times 100. Oops, I pressed ln. Let's do it again. 3902 times, there we go, 0.01252 times 100. I missed a 0. So we get 13,647 if I round to the nearest whole number. 13,647 infected on day 100. Okay, so that was an example of exponential growth, the number of infected people growing very rapidly, even with a smallish percent K value, 1%-ish. So now we're going to do exponential decay. Excuse my cough. So one of the most common times that we use a model of exponential decay is when we know the half-life of a substance. The half-life is the length of time required for 1/2 of the current amount of material to decay, and we call this exponential decay. And just like with exponential growth, there are two equivalent models. One has a half in it to represent half-life, and the other one has base E. So m of t is the mass remaining at time t. M naught, or m sub 0, is the initial mass. T is the amount of time that has passed. In both formulas, t represents time. H is half-life. That's only in the first formula, and it has to use the same units as time. And R is the continuous decay rate. So if you see the word continuous, you're going to want to go with the formula that has the E in it. However, the two equations are equivalent, and you can convert from one to the other just by knowing that R is the ln of 2 over H and H is the ln of 2 over R. All right, let's look at an example using carbon dating. So to find the approximate date that a plant or animal died, we use C14 carbon dating. It's a radioactive substance found in all living things, and we can use it to estimate age, because we know that its half-life is approximately 5,730 years. So let's say we have a bone fragment it's found that contains 20% of its original carbon-14. So to the nearest year, how old is the bone? So its original carbon-14, that is 100%, right? It had 100% at the original time. So I'm going to use the half-life formula because I know they gave me half-life. So I'm going to use the formula that has H in it, this one. The other one has R in it, and I would have to convert, so I'm just going to use the one that has the H. M0, M of t equals M0 times 1/2 to the t over H. All right, so M0 is 100. We start with 100% of of the C14, and then we're going to half it. We want to know how old it is, so we're solving for t. We know H is 5,730, and we're solving for how long until there is only 20% of the C14 remaining. So we want to solve this for t. So first thing I want to do is isolate this exponential expression here. So I'm going to start by dividing both sides by 100. 20 over 100 is 0.2. And then this is 1/2 to the t over 5,730. My unknown is in the exponent, so I'm going to take the ln of both sides. The ln of 0.2 equals the ln of 1/2 to the t over 5,730. And then I can take my exponent and bring it down in front of my log. So the ln of 0.2 equals t over 5,730 times the ln of 1/2. And now I just want to get the t by itself. So I'm going to just remind myself that the ln of 0.2 and the ln of 0.5 are just numbers. So I'm going to divide both sides by the ln of 0.5. So I have ln of 0.2 over the ln of 0.5 equals t over 5,730. And then last, just multiply both sides by 5,730. So we get t equals 5,730 times ln of 0.2 over ln of 0.5. And then that would be approximately, because when somebody asks you how long it will take to do something, you typically don't say, oh, 5,730 times the ln of 0.2 over the ln of 0.5, because that's not very helpful. So we're going to get an approximation for whoever asked us this question. 5,730 times ln of 0.2 divided by the ln of 0.5, and we get about 13,305 years. Okay, so I decided to use the formula that had an H in it because they gave me the half-life. But if I had wanted to use the other formula, I would have needed to know the continuous decay rate R. Right? My other formula has the same M naught is in both, and then they both have a T, but this guy has an R and this guy has an H. So if I wanted to know the R, the continuous decay rate, I just use my conversion formula, ln of 2 over H. So my continuous decay rate R is the ln of 2 over 5,730, which means that R is approximately that's scientific notation, that e to the negative 4 at the end means move the decimal place 4 to the left. So that is 0.000121. Okay, finally, we have one more type of growth model. So in our earlier examples of growth, we assumed a population grew by the same percentage each time period. But in most growth situations, indefinite exponential growth is not realistic. Growth is always limited because of limited space, limited resources. And so growth rates actually start to decrease and level off and approach a maximum level, or a horizontal asymptote, which is known as the carrying capacity for the population. And this is called the logistic growth model. It's used to capture the long-term behavior of a growing population in a closed environment. So the mathematical model for logistic growth is C over 1 plus A e to the negative bt. And we have a graph of a typical logistic function right here. Now, as t goes to infinity, the denominator, a e to the negative bt, okay, so, or a piece of the denominator, a e to the negative bt. So as t goes to infinity, negative bt indicates that, that's exponential decay. So as t goes to infinity, that value gets really, really close to 0. Which means my whole denominator gets really close to 1, and c over 1 is c. Okay? So my horizontal asymptote is y equals c. So the carrying capacity c is in the numerator. All right, so that's it for the demo. Take some time to work through the activities, and when you are done, you can watch the activity for watch the video for anything that didn't make sense.